Hello and welcome to the first episode in this video series dedicated to learning electronics. Today I will be talking about breadboards, sometimes referred to as solderless breadboards, plugboard and prototype board. But before we begin, what's in the name? Why are they called breadboards? Well, in the early days of designing and constructing electronic circuits, people often used a piece of wood, sometimes a literal breadboard with screws, copper nails, metal strips and even thumbtacks that acted as terminals and connection points. They would then solder components together, ultimately fixing their circuit to the piece of wood. This 1920s radio was manufactured by the Signal Company and was constructed on a wooden breadboard. Hence the name that we still use today when working with the more modern plastic substitute that has been around now since the early 1970s. Now, it probably goes without saying, but because breadboards don't require any kind of soldering, they are reusable. And because of this, they're popular with people designing and constructing temporary prototype circuits. Though most modern circuits are still in the design phase and now actually tested using software and various simulation tools before they're then constructed on a more permanent printed circuit board or PCB. Plastic breadboards, though, they still have their place, and they're a great tool for anyone experimenting with building electronic circuits. Even if you make a mistake, you can easily move components around or even start over entirely. Modern breadboards are essentially a perforated plastic block. They come with an array of small square sockets spaced closely together. When a component or wire lead is inserted into one of those sockets, a tin-plated spring clip built into the socket holds that wire or lead in place. Now, these clips are sometimes referred to as contact or tie points and are typically designed to accept 22 gauge wire. However, they will generally expand to fit other diameters too and can accommodate lead diameters from about 0.3 to 0.8 millimeters. Okay, now let's take a closer look at these metal spring clips and how the conductive pathways are actually set out within the breadboard. Now, in order for me to show you what that looks like, I'll need to remove the layer of double-sided tape that's underneath most modern breadboards. Now, that serves two purposes. One, it makes it harder for the metal clips to fall out of the breadboard over time, but it also allows you, after removing that protective layer of paper, to fix your breadboard more permanently to another surface. Now, with that layer of double-sided tape removed, you can see clearly how the metal spring clips are housed within the internals of this breadboard. You can also see how the individual tie points are actually connected to each other in rows of 5 via this hidden conductive pathway. Now, here I've taken the additional step of actually removing one of these sets of spring clips from the breadboard so that you can see more clearly how the component actually fits into the spring clip and is held in place. As you can imagine, over a longer period of time, spring clips will wear out, but that does take a considerable amount of use, and really breadboards are not that expensive to replace. Now that we know how these individual plugs are actually connected to each other via those conductive strips within the breadboard itself, let's take a closer look at the overall layout and design of the breadboard. So let's begin by examining this fairly typical design of a medium-sized breadboard. First, let's take a look at these long continuous rows of sockets in the upper and lower portions of the breadboard, and in this case each are marked by a blue and red line. Depending on the design of the breadboard, the blue line may be black, and they may or may not have a plus and minus symbol indicating positive and negative as appear on this one. Additionally, it's worth noting that these long rows can actually be present within the design without any lines or markings at all. However, they do still serve the same purpose. As you may have already guessed, based on the symbols, these rows are usually reserved for power supply connections. They're sometimes referred to as power supply terminals or bus strips. They're usually used to supply electrical power to your circuit when you connect them to a battery or some other source of power. It should be noted that there is no actual difference between the positive and negative rails, and using them is not a requirement. Constructing your circuits, though, in such a way that they are aligned with the positive and negative rails can make it a bit easier to keep your circuit organized and for troubleshooting when things don't go to plan. As a key takeaway, just remember that the long blue line indicates a conductive pathway along the entire length of that line, as does the red line. Next, let's move our attention to the columns of 5 tie points or sockets that lie between the upper and lower power rails. Remember that beneath each of these columns is a conductive pathway connecting 5 tie points together, just like the one we removed from the smaller breadboard earlier. And of course, exactly the same thing applies to the columns in the lower portion of the breadboard as shown here. Next, it's worth noting the obvious gap running through the center line of the breadboard. This gap represents a clear break between the upper and lower conductive columns of tie points. It also has a very specific purpose though, which is to house integrated circuits. These little chips have 2 parallel rows of pins extending perpendicularly from the rectangular black plastic housing. These chips are able to straddle that centerline gap as shown here, and this area of the breadboard would be reserved for that purpose when needed. The shallow notch running through that centerline is sometimes referred to as the IC trough, and is said to offer some degree of cooling for integrated circuits by providing limited airflow around the chip. Now, there are 2 other common design features with these breadboards that are worth mentioning. One is the letters and numbers that appear on this particular design. You may be wondering about their purpose. Essentially, they're acting as a grid system that allow you to quickly identify specific tie points on the breadboard. This would be useful, for example, if you were following written directions for building a breadboard-based circuit. The other common design feature I wanted to mention were these male and female dovetail notches, which you can use to clip multiple breadboards together and increase your workspace, just like this. As you begin to work on larger and more complex circuits, or if space is becoming an issue, you may want to look into purchasing a larger breadboard like this one. It may look more complicated compared to the medium-sized board that we looked at earlier, but really, they're the same thing. Essentially, we now just have multiples of the same features to work with. You have multiple IC troughs, you have multiple power rails, and you have a lot more tie points that you can use. One thing that is a little different with the power rails on this board though, and is worth highlighting, is that there are breaks midway through some of them, as represented by the broken line here. Watch out for this, but typically you'll see this feature mostly on larger breadboards. I'll leave the discussion of electronic components for later videos, but one final thing we can look at today is something called jumper wire, and we can use jumper wire to make new connections on the breadboard. What I'm holding here is something that's generally referred to as flexible jumper wire. As you can see, it has pins attached to both ends, and these are easy to insert into the sockets of your breadboard. They can be bought in packs much like this one, usually consisting of many different colors, and that's helpful for keeping your circuit layout nice and tidy and organized through color coding. While they're easy to use, as you can imagine, and as you begin to work on more complex circuits, relying just on this kind of jumper wire can make things a little bit messy. An alternative jumper wire option is to purchase packs like this one, which consist of pre-cut lengths of wire that have 90-degree bends on each end. These are purposely designed so that they're ready to use with your breadboard. Additionally, you could buy spools of solid core hookup wire and make your own. This does work out cheaper in the long run than purchasing these kits, and it also means that you can select your own colors and cut custom lengths as needed. To better illustrate some of the pros and cons of using flexible jumper wire over solid core hookup wire, here is a random placement of flexible jumper wire connected to various tie points on a breadboard. Now contrast this to exactly the same arrangement of connections, but now using solid core hookup wire. Their low profile to the breadboard makes it significantly easier to follow the tie point connections, route, and overall placement of each wire on the board. They both have their place, but this is something to keep in mind when designing and constructing your circuits. Well, that's about everything you need to know to get started with breadboards. In later videos, we'll start to look at electronic components and begin to construct basic circuits on a breadboard. I hope you've enjoyed the video. Please do click like and subscribe to the channel if you'd like to see more content like this soon. Thanks for watching.